is that it's the simplest explanation for what we observe in cosmology. In fact, it's the foundation of the concordance model of cosmology. Measurements of type 1a supernovae, of the cosmic microwave background, and of the distribution of large-scale structure, pictured here is the dark energy survey, have given us overwhelming evidence for two stages of accelerated expansion, an early stage of inflation and a second stage, a present stage of dark energy. And the simplest way kinematically to describe each of these is through a quasi-de Sitter solution. Now, the resulting model that involves a cosmological constant, cold dark matter, and inflationary initial conditions is consistent with all observations. And one should bear in mind that the evidence goes very far beyond just the evolution of the scale factor, but includes detailed properties of the perturbations. This is a very tightly woven set of evidence. With that background, we ought to try and understand de Sitter space in string theory, at least in order to understand whether string theory is in fact compatible with the concordance cosmology. We could get more ambitious. With regard to dark energy, we could try to understand whether string theory has enough de Sitter vacua to accommodate the anthropic solution to the cosmological constant problem. And also we could ask whether it produces a better solution. And with regard to inflation, the signatures imprinted in the CMB depend on the physics of the Planck scale, specifically on certain Planck-suppressed operators in the effect of action. This effect is best known and most dramatic for primordial gravitational wave perturbations, but it's totally general. So understanding inflation requires understanding inflation in quantum gravity. And so taken all together, this gives us a really powerful link from string theory to observations. The plan for the talk is to overview the nature of the problem. I'll spend most of my time talking about the KKLT scenario. This is due to Kachru, Kalash, Linde, and Trivedi, now 16 years ago. And then I'll say what I can about other constructions. Thinking about quantum gravity in de Sitter space is challenging, and I won't be able to tell you anything new today about how you should do that. Rather, I'll focus on just constructing de Sitter 4 solutions. Ineffective field theories derive from compactifications of critical superstrings. There's a lot more in the study of de Sitter in string theory, but this is the scope that I'll restrict to. This is the part that we understand more or less the best. I'm going to require that the four-dimensional curvature is small in string units, and so I'll derive and use an effective field theory that's valid well below the string scale. As a brief remark, it has been observed, particularly by Banks, that it's conceivable that effective field theories like this are not even meaningful in quantum gravity for fairly deep reasons. I'm going to assume that if one derives an effective field theory correctly from string theory, then the vacua of that EFT descend from vacua of the full string theory. Now, the approach will be as follows. We'll start with 10-dimensional supergravity plus a collection of localized sources from string theory, d-branes, orientifold planes, etc., and we'll obtain thereby a four-dimensional gravity or supergravity theory. So depending on what we start with in 10 dimensions, we'll have a collection of possible terms here, and in 4 dimensions, among other things, we'll arrive at a Lagrangian for some scalar fields, moduli fields. And the task is to figure out what that Lagrangian is and whether it has de Sitter minima. Now, a conceptually easy approach that's simply not practical at present is the following. You could start with a solution that preserves n equals 1 supersymmetry in 4 dimensions, for example, type 2 on a Clabia orientifold. So that part is easy. And then you would try and directly compute the 4-dimensional effective theory to some high order in the alpha prime and G string expansions. You would then try to exhibit de Sitter solutions in the EFT, including only the penultimate terms in each expansion, and show directly that the last terms, the smallest ones that you were able to compute, are in fact strictly subleading. The reason we can't do that is just that we're not very good at computing completely and systematically all the terms in these expansions. Lacking that, we have to apply further approximations and look under special lampposts. The one that I want to stress today, which is a pretty standard paradigm in the study of compactifications of string theory and their phenomenology, is an attempt to seek parameter regimes in which various sectors decouple. Decouple into modules that interact weakly. What you can then do is analyze the modules in isolation and then reintroduce the awareness of their interactions. So I'll give lots of examples of this. As an overview, at present, many of the modules, many of the constituent pieces of a de Sitter vacuum are actually quite well understood. And the final assembly of these things into a complete solution is the key challenge that we're presently facing. So before getting into the KKLT case, let me give a few more remarks by way of overview of the status. By now we have many scenarios for constructing de Sitter vacua in effective field theories that are derived in compactifications of string theory. However, we have no incontrovertible example. On the other hand, many highly non-trivial tests have already been passed, as I will review. And to me, the remaining difficulties appear to be purely technical. But one can't be sure until going through that. It's absolutely essential to understand that this challenge is not unique to de Sitter vacua. At the standard that we are currently demanding in the literature on de Sitter, we also do not have a construction of the standard model plus Einstein gravity in string theory. The difficulty is simply that non-supersymmetric compactifications are difficult to analyze. We don't have a lot of tools, but we should not conclude automatically from this that they don't exist. So now on to the main object that I'd like to review, the construction of KKLT. So I'll begin by reminding or telling you what happened in the initial construction, and then I'll review what has happened in the last few years with regard to its status. We're going to consider a compactification of type 2b string theory on an orientifold, which I'll call X, of a Calabi-Yau threefold. We're going to include quantized three-form flux, an n=1 pure super Yang-Mills sector on some collection of D7 branes, a warped deformed conifold region, i.e. a Klebanov-Strassler solution, that contains one or more anti-D3 branes. And the claim of KKLT is that in a suitable parameter regime, these sources can yield a metastable de Sitter vacuum, and the corrections to the approximations are small. Let me point out that a great deal of work has gone into a closely related scenario that builds on the same ingredients. This is the large volume scenario. It works in a slightly different parameter regime in the Kähler moduli space, and also crucially includes the alpha prime cubed Riemann to the fourth correction to the Kähler potential. Due to limitations of time, I won't be able to say much about that, but a lot of rather successful work has gone into finding de Sitter constructions there. So in slightly more detail, the setup is as follows. I'll take an ansatz that includes a four-dimensional metric G mu nu. This will be, for example, de Sitter. GAB is the metric on X. I have a warp factor A, which depends on the coordinates on the internal space, and a breathing mode U, an overall dilatation of the space that depends on the space-time position. For the purpose of this exposition, I'm going to take H4 of XZ to be generated by a single divisor sigma, and I'll imagine we've picked some quantized flux. The moduli in this theory are then the axiodilaton, H21 complex structure moduli, and by assumption here, a single Kähler modulus that's related to the breathing mode. The effective n=1 supergravity theory in 4 dimensions for these moduli is well known. There's a classical Gukov-Vafa-Witten superpotential and a Kähler potential that looks like this. Now, if we take this theory and we try and solve the F-flatness conditions for the axiodilaton and the complex structure moduli, we find that for generic choices of G3 flux, the solutions to those conditions are isolated. That means that the axiodilaton and complex structure moduli are fixed. They receive large supersymmetric masses from the flux superpotential. Below the scale of those masses, the only thing in the effective theory is the Kähler modulus T, and as far as the Kähler modulus is concerned, the superpotential evaluates to some constant. This theory has the property called no scale. The F term for the Kähler modulus is non-vanishing except at infinite distance in the field space. The F term potential is 0, so supersymmetry is broken. But the Kähler modulus is unfixed, so this is certainly not a de Sitter vacuum. Now we're going to think about the effects of a stack of D7 branes supporting a pure super Yang-Mills theory. We could just as well think about Euclidean D3 branes wrapping the divisor sigma, But for the purpose of the presentation, I'll speak only of the gaugino condensation case. So these 7 branes generate a gaugino condensate superpotential that looks like this. And once we take account of the relationship between the Kähler modulus T and the gauge coupling function on the 7 branes, we can write the non-perturbative superpotential as an exponential in T. The prefactor here depends on the complex structure moduli, but not on T. So in sum, the superpotential has a constant piece and an exponential piece. And the result of KKLT is that this supergravity theory has an ADS4 minimum that's supersymmetric. If the constant superpotential is sufficiently small, then this minimum occurs at large volume, and the mass of the Kähler modulus is small compared to the mass of the complex structure moduli in the axiodilaton. And it's been argued and then shown in examples that sufficiently small W naught does occur for some of the exponentially many choices of quantized 3-form flux. I'll say a bit more about that later. The last step in the construction is to introduce P anti-D3 branes at the tip of a Klebanov-Strassler throat. The Born-Infeld plus Turin-Simons action for these anti-branes is equal to twice their number times the tension of the brane times the power of the warp factor and the power of the breathing mode. In a non-compact throat, this configuration gives, as Kotru, Pearson, and Verlinde showed in 2001, a metastable supersymmetry breaking state. In a compact throat, the anti-D3 branes affect the equation of motion for T because they cause a slight dilatation of the overall space. This is the decompactification instability. In principle, they could also affect the gaugino condensate itself. Now, to the extent that the anti-branes affect the gaugino condensate only by contributing to the equation of motion for T, namely only by causing a small dilatation, which we'll come back to, then it does follow that the total potential in 4 dimensions is the sum of the Born-Infeld plus Turin-Simons part from the anti-branes and the F-term potential for the moduli. The key result of KKLT is that this theory has a metastable de Sitter minimum. Now, there's a lot of questions we should ask. This concludes, by the way, the review of the construction itself, and now I'm going to tell you what has been learned since that paper was written long ago and what we know now. You really ought to ask, concerning moduli stabilization, do there exist consistent global models in which you can find quantized fluxes that give a small classical superpotential? Do there exist models in which one finds the right sorts of Yang-Mills sectors and Klebanov-Strassler throat regions? With regard to the antibrane, you might ask whether antibranes can be described with a supersymmetric action. You ought to ask whether decompactification is the leading instability that the antibranes cause. You might ask whether antibranes and the gaugino condensate indeed interact weakly, as I temporarily assumed. And you could also ask whether the de Sitter solution can be described in more 10-dimensional terms rather than as a solution of a 4-dimensional EFT. The answer to all of these questions in the recent literature is yes, although there's room for improvements in virtually all of them. Now, a question which has not yet been answered is whether one can exhibit an explicit and fully controlled compactification that unifies all of these components in one place. That is certainly a work in progress. So this is what I meant when I said that the modules are under good control. We understand the pieces in isolation, and the task is to find one compactification where all the pieces fit together. So let me tell you what I can about most of these individual modules. First, concerning the supersymmetric moduli stabilization, do there exist consistent global models that achieve that? Supersymmetric ADS. Well, yes. There are detailed studies of this by Danev, Douglas, Floria, Grassi, and Kotru some years ago. And I won't take you through all the details, but for example, they pick some Calabi-Yau threefold orientifold like this, and then they checked that the gauge group that showed up generated a gaugino condensate. They found a complete set of Euclidean D3 brane contributions to the superpotential, and they verified that all the known effects that can cause such a superpotential to develop a zero were absent. They then checked that one could find quantized fluxes, specific values of the quantized fluxes, for which, so this is the superpotential they had, for which the corrections to that superpotential and to the whole EFT are at the percent level and smaller by a very conservative estimate. Now, you could very reasonably say that you would like better than 1% control. This is the status as it is now. No one, I think, has tried particularly hard since 2005 to do better than this. It would certainly be a direction where progress would be valuable. Nevertheless, this is a very comprehensive study of these corrections, and it was rather conservative. Concerning antibrane uplifting, you could ask whether antibranes can be described supersymmetrically. A lot of work has gone into this, and the answer is yes. If you use constrained multiplets appropriately, you can actually write a complete supergravity action, as was recently achieved by these authors. One sees that supersymmetry is spontaneously broken. This is useful for describing the couplings of antibranes to the background fields. Still about antibranes, an important question, again, that has been much studied is whether there are instabilities or singularities coming from antibranes. Question driven particularly by initial work of Bena, Granja, Hamagi in 2009 is whether there are singularities arising in the fluxes near anti-D3 branes, unphysical singularities. The answer was beautifully given in this paper. Yes, if the ansatz that's taken is too restrictive and excludes the possibility of the antibranes puffing up in the flux background into an NS5 brane configuration, as the Myers effect forces them to do. Once one considers an ansatz that is not too restrictive, then there's no requirement, there's no guarantee of a singularity. And in that complementary regime, there was an impressive study by these authors at finite temperature. So they heated up the configuration, and they found pretty clear signatures of compatibility with the original analysis of Katri, Pearson, and Verlinde, and with the analysis of Cohen-Maldonado et al. I'll summarize these last authors. Quote the summary that they themselves gave. We regard this as very strong evidence for the existence of the metastable states, since by now they've been argued in rather complementary ways. The last thing I'd like to say about KKLT concerns a 10-dimensional description. Now, in some ways, this is optional. You might ask, you don't have to ask, but you might ask whether de Sitter solutions of this form can be described in an intrinsically 10-dimensional manner. Remember that the construction that I just described to you involves beginning with 10-dimensional ingredients, antibranes, D7 branes, dimensionally reducing, studying the gaugino condensate superpotential in the 4-dimensional theory, and studying the equations of motion of the 4D EFT, and exhibiting a de Sitter vacuum. That's fine, but you could conceivably complain this is not a 10-dimensional construction, and there are some things you can do in 10-dimensional constructions in the spirit of extensions of the Melisende-Nunez type constraints. No-go theorems that you could try and prove if you had access to 10-dimensional results. So we could try. And as I'll report, we've succeeded, a number of groups working in a coherent manner on this, have succeeded in exhibiting a 10-dimensional construction. So that's great. One can check for consistency that way. So what we're going to ask is whether the same vacuum that I've reviewed now, the 4-dimensional vacuum, follows from the 10D equations of motion. The 10D equations of motion that are relevant, here's a version of an arrangement of the Einstein equations and Bianchi identity. This is the 4-dimensional curvature, and that equals a contribution from the antibrane potential plus a contribution from the gaugino condensate. What I need to do is explain to you what the gaugino condensate stress energy even means, where it comes from, and how it's computed. What I mean by giving a 10-dimensional construction is to derive from first principles what this stress energy of the gaugino condensate is, and show that when I substitute its value in here, the 10-dimensional equations of motion force the 4-dimensional curvature to take exactly the value that it takes in the EFT computation. In other words, the 10D and 4D calculations match. So we have to go back to the D7 brane configuration. An old result of Camara, Ibanez, and Uraga tells us that on a stack of D7 branes in a flux background, the D7 brane gauginos get a mass from the flux, a soft mass. You can read that two ways. One is that this is just the mass term, but another is once the gaugino bilinear is non-vanishing, this term corresponds to a D7 brane localized source for G-flux. In other words, gaugino condensation sources flux. That may seem a little bit far-fetched. Let me give you a consistency check of it. We're going to consider probing this system with a D3 brane. Not an anti-D3 brane, a D3 brane. And it happens that we know a lot about the potential for the position Z of a D3 brane in a compactification like this, it turned out to be necessary to know that to study models of inflation with D3 branes, and so there's been a fair bit of work on this. The upshot of which is that we know how the non-perturbative superpotential depends on the D3 brane position. It's actually through a Pfaffian prefactor. We also know, due to work by de Wolf and Giddings, how the Kähler potential depends on the D3 brane position. Knowing those, we can write down an F-term potential. I'll spare you the explicit expression, but it's very well known. And now the consistency check is the following. The other calculation we could do is to take seriously this coupling, include the gaugino bilinear, solve the 10-dimensional equations of motion, we will find flux. Flux comes out of the D7 brane into the bulk. Now we solve the full nonlinear equations in the bulk, and we find some solution. We now probe that solution with the D3 brane and evaluate the probe Born-Infeld plus Chern-Simons action. That's a purely 10D calculation, with the exception of the fact that I'm introducing a gaugino bilinear expectation value. That's what's on the left-hand side, the Born-Infeld plus Chern-Simons potential of a probe D3 brane in the G-flux background sourced by the Camara-Ibanez-Aranca coupling. And what one finds is that that exactly agrees with what was computed in the four-dimensional theory. Namely, there's a perfect match between the four-dimensional F-term potential from the non-perturbative superpotential and the 10-dimensional dBi plus Chern-Simons potential due to the G3 flux. In sum, this is pretty compelling evidence that there's some meaning to viewing the gaugino condensate as sourcing flux. Now, what we wanted to do, though, was to compute the stress energy associated with the gaugino condensate, not compute the potential for a probe D3 brane's motion. So what we'll do, we have a term in the action, so now we can just vary that term in the action and get a stress energy. When I do that, we find it is such that the 10-dimensional equations of motion force the four-dimensional curvature to take exactly the KKLT value in the supersymmetric configuration without antibranes. And if we repeat the calculation in the presence of antibranes, again, the 10-dimensional equations of motion cause the four-dimensional curvature to take exactly the KKLT, now de Sitter, value. So the match is exact, and the upshot is that there's consistency between the 10D and 4D calculations. Let me highlight that a lot of these results depend on work of my student Manki Kim, who's here. Okay, so as a status summary of KKLT, there's no evidence of obstructions or inconsistencies of any kind, but we are still awaiting complete and explicit compactifications. Now, in the last couple minutes, let me say a few words about constructions in other string theories. In the heterotic string, many, many years ago, Deinröhm, Seiberg, Witten effectively constructed a superpotential that's very similar to the one that we've been discussing today. It has a constant term from flux and a non-perturbative term from gaugino condensation. The trouble is, with a real flux, flux quantization prevents this term from being small. And so it's very difficult to stabilize at weak coupling. Also, intrinsically, in the heterotic string, the constructions are global, so they're not modular. We don't have the freedom to build separate pieces and stick them together as easily as we do in type 2 constructions. In particular, there's no module for metastable supersymmetry breaking in de Sitter at a parametrically low scale in string units. With regard to type 2A, here there's been a great deal of work. I refer you also to the talk by Tomasiello this afternoon. Classical flux compactifications are already interesting, so that's great. We can work with just classical ingredients and get very close to or even get to de Sitter vacua. Now, if you study Calabi-Yau compactifications of type 2A with H3 flux and Ramon-Ramon fluxes of these sorts, and D6 branes and O6 planes, you can prove a no-go theorem. There can't be de Sitter vacua. Once you include negative curvature, you can certainly find de Sitter critical points. What remains to be determined is whether one can find satisfactory vacua. Silverstein has argued that in nil manifolds with fluxes and certain KK monopole contributions, you can actually find a de Sitter vacuum. Now, I should stress one basic problem in all of these type 2A constructions is what's called smearing of O-planes. At a technical level, people are not yet capable of solving the equations of motion in the presence of O-planes where they actually sit. And so instead, people integrate the equations of motion across the bulk and pretend the O-planes are uniformly distributed and solve those integrated equations. What remains to be determined is whether one can find solutions with localized O-planes. And again, Alessandro will tell us some things about this. So let me conclude. There's considerable promise for exhibiting controlled de Sitter vacua in effective field theories derived in solutions of string theory. In the last years, we've seen steady progress. We've seen increasingly precise and explicit computations. and many very highly non-trivial tests have already been passed. At the same time, we don't have an incontrovertible example. I don't think we have much prospect of finding de Sitter at arbitrarily weak coupling. Learning to control non-supersymmetric solutions of string theory is the central challenge. Thank you.
Yes, thank you very much for a great talk. Questions? Okay, yes.
Thank you for the nice review. I have a comment and a question. So first the comment, you raised the question of whether you can have a supersymmetric description of the anti-D brane, and you said that this can be achieved, and this is confirmation for the scenario, using constrained superfields. Did I understand correctly that that's what?
I didn't say that it was a confirmation of the scenario. I said only that if one asks, can it be written in such a way, then the answer, according to Cribiori et al., is yes. And what I said that that was particularly useful for is as an efficient way of packaging some couplings of the antibrane.
Okay, so my comment about that is that the whole point of the constrained superfields is that you can turn any non-supersymmetric theory into a supersymmetric theory.
Yes.
And therefore, they should not be viewed as evidence for anything.
Totally agree.
So now for my question. At various points in your talk, you use the word small or the word large. For example, small W0 or large volume limit.
Yeah.
Which of them are parametrically small so that we really know what we are doing, and which of them are just happen to be small, like 1/3 or 1/4?
Right, good, yeah. So in the entire question, so first with regard to the supersymmetry breaking and the constrained superfields, I completely agree. The utility of those works is in allowing us to more carefully, in my view, is allowing us to more carefully study how antibranes interact with other fields, which after all we're already formalizing in a supersymmetric manner. It's not a check of the validity of the construction. It's useful to do it, but it's not a check. Now, with regard to parametric control, this is the key challenge. And there's a fundamental restriction which one is always faced with, which is the following. If, in fact, there's a finite landscape of isolated vacua of whatever sort of string theory, then there are no strictly parametrically controlled calculations of any kind. So let's back up, though, and just ask, to what extent can one make the numbers more or less as small as one can reasonably want versus arbitrarily small? And one test of that, for example, is the following. So we can go back to the work of Denef et al. In the case of supersymmetric stabilization. I think the litmus test is whether the known additional corrections are small enough to appear safe. So this is marginal. The known corrections were evaluated. They evaluated, for example, higher instanton corrections. They evaluated higher curvature corrections, and they were at the percent level. That's not great. Certainly not. But they're also not, a half or something like that. And I think this is the measure. One doesn't necessarily want to single out one parameter and say that numerically it has to be a specific thing. Rather, we just want to compare one term in the expansion to the next term. Here, the test is percent level for the next terms in the expansion. I think it's an important direction for people to do better and push this kind of thing.
So I also want to follow up on that. The parameter which is small and drives everything here is W0.
Correct.
Right? And everything is small if W0 is arbitrarily small.
True.
Now, you say that it's not arbitrarily small. Okay, maybe we can live with that, maybe not. But as W0 varies, the microscopic construction varies dramatically. So W0 being, say, 1/10 and 1/11, the underlying geometry is completely different. So it's not even smooth as a function of that.
Certainly not. It's a discretrum. So if one wants to come up with a more compelling answer to your question of how controlled these things can be, the task really is the following. Pick quantized fluxes that make W0 small, then pick another value of quantized fluxes that make it smaller, and there's no sense in which you can interpolate from the first to the second. You just have to find a collection of isolated things and look at each of them until you find one that's satisfactory. There's no smooth connection. This is, however, not, I think, something specific about this kind of construction. It's something that's quite general to landscapes of isolated vacui in n equals 1 and n equals 0 theories.
Okay. Yes.
Yeah, I'm not so sure there is a great consensus in the literature on the Gaugino condensate together with the SUSY breaking terms. And in particular, there was a back of the envelope argument by the Hamburg group that if you put a Gaugino condensate and then you want to break supersymmetry in the infrared, there's actually an order 1 communication because the Gaugino condensate blue shifts to the tip as an order 1 back reaction effect.
No, I mean, as you probably remember from the discussions at Geneva, they were agreeing with that is not presently an issue. As I understand their calculation, that blue shifting was what would have to happen for one of their indirect arguments to hold. And what ended up occurring is that when the equations are reorganized in such a way that the breathing mode is incorporated properly, one doesn't anymore have to postulate that effect. Now, if you directly compute and you ask, is there a mode that can create such a blue shifting, there isn't one. And I think that Jakob, for example, agrees with that now. I'm not yes, okay, getting thumbs up, yeah. So I think the situation is not completely settled because nobody has written down in great detail a configuration of the condensate and antibrane and done the calculation in between. But their original paper, if you look in just their appendix, the spectroscopy there strongly supports there not being blue shifting, which was what was paradoxical, in fact.
Yes, Sandeep.
So I have a question and a comment. Thanks a lot, Liam, for this very nice review. First of all, as far as the interactions between the Gaugino condensate and the antibrane are concerned, you can try to write down higher dimensional operators, as you know very well, and they don't suggest any kind of instability, etc. They're typically all under control. That was just a comment, but you might want to.
No, that's absolutely right. Yeah, thanks. So you may note that this is one of the things that I didn't review the status of. Okay, and the status is as follows. Antibranes will for sure affect the Gaugino condensate because they cause a slight dilatation of the space overall. That's unavoidable. It's through the overall volume of the space. One can't hide from that. Now, you could ask, if I consider antibranes at the bottom of a Klebanov-Strassler throat and D7 branes near the top of such a throat, what are the leading interactions between them besides that breathing mode interaction? And as you say, what one needs to do is find the lowest dimension operators in the CFT that can mediate the couplings in question, right? That's been done. And the result is that there are no operators that mediate problematic interactions. In fact, this was first observed by Moritz, Redlaz, and Westphal, and their remark was that they were not able to find a way to envision the Gaugino condensate superpotential changing in the presence, the stress energy here of the Gaugino condensate superpotential, they couldn't see how including an antibrane could change that. In other words, the antibrane was sequestered from the condensate.
But if I can just quickly follow up with a comment, which is, this is ugly, but given your conclusions, which I agree with, which is that the individual modules seem to be well under control, maybe even in pairs, but we need to be able to put them all together in a convincing way. Do you think putting this problem to a large computer or an effort like that is called for now?
I think so.
It's a bit ugly, but I want to
well,
ask
the first step would, I suppose, be for some people to try and do it with pencil and paper first. And there really has not been a lot of work on compact global constructions of KKLT type since the Deneth et al. Work in 2005. There's been a lot of work on these different modules. And in the literature, I have not seen people try to glue them together. I don't see why that's an insuperable problem. You're right, if one starts asking questions about, for example, whether large Klebanov-Strassler throats can be embedded in spaces with small or large numbers of Kähler moduli, you might need explicit Calabi metrics, and so then that's indeed a numerical problem. But no, I think all of these things are more or less in reach. In fact, let me also highlight with regard to small W naught. Again, no one has tried very hard. It's a shortest lattice vector problem. It's computationally expensive, but no one's just paid up. I think progress can be made in that direction.
Okay, I think I'm forced to end on this optimistic note. We can have much more discussion of this in the coming months, years. Thank you very much, Liam. Yeah.